So thank you for inviting me. Yes, my name's Nerea Uri Carreño, and a little bit about me. Well, first we're gonna I'm gonna have a presentation very biased towards Denmark. That's how we have decided to divide our content today. Amanda, the speaker after me and myself. So I'm gonna bring you some lessons learned from Denmark and the topic of greenhouse gases. And most of my work has been done on N2O, so it's gonna be very focused on N2O and very focused on Denmark. And I was told that the audience of this webinar is not only wastewater people, so I try to keep it pretty high level, and I'm gonna um, start high level, maybe go into a little bit of the learnings, and then bring it back to high level, and hopefully bring some questions that could be interesting for discussion. So myself, I worked.
Nerea, can I
Yeah.
shortly? So we don't see like your slides. I think it's frozen. So maybe if you
Oh,
can try to reshare your slides.
yes. Thank you for letting me know. Um, okay.
Yeah,
Now?
perfect. Yeah, perfect now.
Okay.
So go ahead.
Okay. Well, there was nothing in here that you had to look at, so no problem. Yes, so a little bit about me before I start. Um, I was I'm still a young water professional for 2 more weeks. Uh, so I really appreciate these initiatives. Very involved with young water professionals in Denmark. Um, and Denmark is where I've worked my whole career for, I think now it's going to be 12 years. And I started to utility, and a very progressive, very unique utility that had a very ambitious vision. And it's been a true pleasure to work with them for a decade. I've always thought I had the best job on the planet. And a lot of my work focused on N2O, not everything. So I do, it's not, N2O is not my only focus. I also love to work with other technologies and aspects of wastewater treatment, but it's a big part of it. And I've been involved in many of the projects that have come out of these initiatives in Denmark, working with greenhouse gas emissions. And for the past 8 months, um, I have been an independent consultant, working independently for other utilities and other companies, and again, partly on this topic. Gonna start from the very beginning, not go too much into the biochemistry of everything, but just to get these started, a wastewater treatment plant, for those of you that are not wastewater people, it's like a tiny river. So we try to make everything that would happen in a water body, all the biochemistry that would happen, we try to make it in a very compact space so that those reactions do not happen outside of the wastewater treatment plant. And so we get carbon, phosphorus, and nitrogen into a wastewater treatment plant. I always used to say when I gave tours at the wastewater treatment plant, we never ever talk about feces or urine. For us, everything is carbon, phosphorus, and nitrogen. And we want to get that out of the water. So our main product is to have clean water at the end, and then hopefully get some of those nutrients ready to be recovered in the sludge or as pure products if we can do that. And then some of it is gonna get transformed with these mostly biological reactions. And we're gonna try to produce biogas in some wastewater treatment plants as well. When we do this, not unintendedly, we're gonna have three byproducts mainly that are greenhouse gases. We're gonna have first a lot of CO2, which not usually, which we don't account for because we say it's not from fossil fuel origin mostly. So for now, at least for now, we don't really pay a lot of attention to it. That might change. Then we've got methane, unintended methane production, and then we have unintended N2O production, which can be really, really significant. We're gonna focus on Denmark today, and the whole Nordic region has very green electricity grids and has very ambitious climate goals, and that has meant that it's meant a lot of driving force, a lot of funding, a lot of support institutionally into developing this topic. And specifically for Denmark, we have a commitment to become climate neutral by 2030, and everybody is expecting of these new N2O regulation, probably the first one in the world that should have come this year, but I think we're all a little bit expectant. I'll talk a little bit more about that later. So when we talk about decarbonizing wastewater treatment plants, the way we do this is by dividing into different emission scopes. So scope 1 will be everything that is directly emitted at the wastewater treatment plant. So everything that you can actually go and measure. It's gas that is coming out of your reactors, your anything. That's scope 1, direct. Then we have scope 2, which is the CO2 that's associated with using electricity. So we use a lot of aeration, for example, in wastewater treatment plants that uses a lot of energy. If the energy comes from, let's say, coal, there will be a lot of CO2 associated with that. If your electricity consumption comes from nuclear or hydro, then there's going to be very little. And scope 1 and 2 are operation stage, and that's usually what most utilities have targets for. Scope 3, it's still under development. It's more complex to calculate, and it includes everything, the pipes that we put in the ground, everything that we use for construction, what we do with our sludge, the chemicals that we use at the treatment plant. And then we've got scope 4, which I think to me right now is the most exciting, which is it is not well developed, and there's no clear standards for this yet, but it's I like to think of it like it's the consequences of your actions. So when you make decisions and you take one path or the other, and your consequences have an impact, it is the consequences of the impact. For example, if we produce biogas, we are replacing another source of fuel. So is that an environmental impact? That will be scope 4. And I think this is the one that probably will allow for synergies and collaboration with different parts of the water sector and even outside. So under development, but I think to me very exciting. I'm gonna show an example. This is from Vincent Sud, the utility that I work for, just so that you can see what one of these will look like in Denmark. And you can see for scope 1 and 2, scope 1 direct emissions, mostly N2O by far. You can see 4,000 tons out of 5,000 come from N2O emissions, and this is using emission factors. So just giving a number for that N2O and not actually measuring how much it comes out of the wastewater treatment plant, way larger than electricity. Like I said, the electricity grid is already pretty decarbonized. And then I think it's one of the first utilities, at least that I've seen, making an attempt at calculating scope 3 emissions and how much it goes into that. And it's not insignificant for sure. And then also an attempt to calculate scope 4, what happens when they use biogas for energy production. Also, they build, well, not build, they create forest to protect groundwater. That also has an impact. So that'll be in these scope 4 emissions. I think N2O has played such a huge role because it has a global warming potential that's almost 300 times. Depends on there's yeah, the number that you use, but very close to 300 times larger than CO2. So even a little bit of N2O can have a huge impact. These are a couple of tools that I put on my website where you can see, what is the difference between scope 1 and scope 2 emissions for a wastewater treatment plant, depending on how intensive the carbon is in the grid. So are they using coal? Are they using is their carbon intensity 800 or is it 100? Are we in France or are we in Poland? And then what is the N2O emission factor? How much nitrogen are they removing? And then let's see, you can have a look at whether scope 1 or scope 2 has the more impact. And it's usually scope 1 that plays the biggest role. And then once you get into scope 1, I also put a little tool where you can look at, N2O really plays such a huge role when you look at this specific unit, and you look at, depending on how much N2O you are emitting per every molecule of nitrogen that you are treating, the comparison between that and the energy that you use for aeration, it's really huge. So that's one of the reasons why there's been a lot of work on N2O in Denmark over the years, lots and lots of funding. I put the website where all of these reports are, because there's like such a wealth of case studies over the years. I started uh, I started right when Unisense was
Sorry.
Wait, I will.
Okay, yeah, exactly. Good. No, she's muted. Sorry, Nerea, for the interruption.
That's okay.
This was unintentional.
It's okay. When Unisense was developing their sensors. Oh, I also realized I think I have to speed up. So some of the consequences of this is that the emissions factors really have changed, and Denmark now has their own emission factors based on data that have been collected from the wastewater treatment plants. Again, this is some of the first work back in 2013 when Unisense was developing. They already had microsensors. They were developing full-scale sensors. There's this article in the news. I think it says Avant Intersud, the utility, had the ambition to become carbon neutral by 2014. So obviously that did not happen, and of course still hasn't happened. I think we have developed our understanding quite a lot in this past decade. These are some of the results from this effort, where Denmark wanted to develop this new emission factor and understand what is the N2O from. Can we get an average N2O from the whole country? Like, are our wastewater treatment plants more or less similar? And yeah, we can talk a lot if you want on the discussion about emission factors also with Amanda. They wastewater treatment plants have very, very different N2O emissions. And it varies a lot. If there's some, and this is the Mule is the treatment plant that I worked at, so we can also talk about why these were like so large at this point in time. So also something that we have seen in Denmark quite systematically is our side stream anamox have larger emissions. So that's also something there's been quite some work on. Commonalities between Danish full-scale studies over the years has been, for sure, seasonality. That's something that we see, and that's something that we see all the places in Europe too, where wastewater changes temperature, where wastewater treatment plants change their SRT quite a lot. And we can see there's very strong, usually early spring, changes in wastewater treatment plant. This is results from Aarhus in the left. These are results from Ejbymølle in the middle. And what we see is different emission factors throughout the year, different emissions from year to year, and different emissions from tank to tank, even though tanks that are supposed to be exactly the same. So quite a lot of heterogeneity and this very strong seasonality. There's this new paper that recently came out from Delft that I think it's probably the one that has gotten closest to understanding why this is happening and linking the microbial community to this. But there's been some work also in Denmark about this. Side stream Anamox, I mentioned when I started working, side stream Anamox was the 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 best. It was like so exciting, and everybody, was really excited about this technology. And then we started seeing um it had maybe more into emissions that we expected, and now it's become kind of a villain. Maybe, yeah, maybe a little bit. Um Yes, we'll see. That's up for discussion later. But that's something that I've personally worked on, and others in Denmark too. These specific types of reactors that we have at wastewater treatment plants, that are very good at treating wastewater in a very intensive way, very energy efficient way, but that have associated typically more N2O emissions. But we've also seen that we can use control and mitigation strategies to bring that down. So that is a lesson learned for sure. This is a couple of papers that we just published last year on controls for side stream Anammox. Something that I've also been very excited to work with in Denmark that had, I believe, the first full pilot trial of this is N2O is in the gas phase. So one possibility is we can destroy N2O from the gas phase instead of trying to control it and trying to manipulate it so it doesn't happen. So that's what we tested in this project, which was um, um, where we tested this technology in 3 wastewater treatment plants, and quite successful for specific cases. The full report is still not finished, but I think it's a definitely interesting, and it has a potential for the future for sure, as a way of getting rid of these emissions at wastewater treatment plants. Something that I've also been very excited to work at, and something that also first came out of Denmark, was work on N2O emissions from MABRs. A lot of information on this slide, apologize. But when we get to more intensive technologies in wastewater treatment, we have the risk that we get more and more N2O emissions. So this is a technology that has shown potential for combining this intensified technology. Like, we want to do wastewater treatment plant the least amount of volume possible, but we also want to have low N2O. So it's part of this trend, I believe, on trying to not only mitigate, not only react on the emissions that we have, but trying to, and I think Amanda's doing a lot of work on this, like trying to, from the beginning, can we design better so that we have a lowered risk of high N2O even before the systems are in place. A little bit of Danish central legislation, because this is probably something quite unique. Um, and and um, and it's interesting because they made an effort on estimating how much this was going to cost wastewater treatment plants and taxpayers. Like, how much is it going to cost if we make all wastewater treatment plants larger than 30,000 P, quantify their emission, and how much is that going to cost if we use gas hoods, which is one of the main types of technologies we can use to quantify emissions, versus what would it cost if we use liquid sensors. And also, very interesting, they made an effort into calculating how much is this going to cost if we use optimization, so changing the controls at the wastewater treatment plant to reduce N2O, versus just making larger wastewater treatment plants, because we know large wastewater treatment plants have very low N2O, because we've got the microorganisms in there are not stressed. but as you can see, that will be very, very costly. And again, very nice that we see some values. I think this is some of what we are lacking right now, is having actual numbers of what would cost us to mitigate N2O, so we can put a number on per ton CO2. And in here, it's like you can see this a huge variation from 7 to 1,000 euros or USD per ton CO2. But yeah, so some case might be really, really cost effective. If we are looking at expanding wastewater treatment plants, probably not a very good business case in any regard. Before I leave to the discussion, I wanted to bring it up again and bring some questions for the young people in the audience, especially. So we think about this from a different perspective. The utility I worked for was one of the first ones to do an absolute sustainability assessment and look at, how is the wastewater treatment plant impacting the planet in different categories, and like where is the largest contribution. And for the wastewater treatment plant, it was for sure the nutrient discharge. So both phosphorus and nitrogen discharge is by far what contributes the most to crossing those planetary boundaries. And again, very specific for Denmark, for the North Sea and the Kattegat. The level of nutrients in our coastal areas is unsustainable, and this is what our fjords look like. So in the future, we're gonna look at conflict of interest versus so we're gonna have push for more nutrient removal, and we're also at the same time gonna have to do this while being carbon neutral. So yeah, this is an area that's gonna come for sure, this conflict of interest. Here I just got 4 examples of bringing these questions into wastewater treatment plants and greenhouse gases, and different ways that people have looked at these. Like one of the questions that come up, for example, is, when we have these Anamox reactors that I said can have very high N2O emissions, how is holistically, what is the impact of these technologies? And again, if we look at the nutrient removal, it seems like, it is overall, if we disregard climate change, it's overall a good idea to remove nutrients always. This is also a new paper, this one in water research, looking at what would happen if we didn't have wastewater treatment plants. Well, the N2O emissions from that nitrogen, that those conversions are going to happen in the river anyway. So is it better to have a wastewater treatment plant or not? The third one here is looking at the N2O from a global perspective. Where does N2O in the world come from? How much of it comes from wastewater versus other sources? And that links to the fourth one, which is N2O emissions that are mitigated from other sources like fertilizer production. This study can cost less than €1 per ton CO2. And we're looking at reduction strategies sometimes at a wastewater treatment plants that, for what I have seen, and again, there's almost no data on this, might be in the hundreds of dollars per CO2. So again, I think this is going to be very interesting in the future to look at where do we get the most benefit overall? How do we do the most good? I think I'm over time. But yes, there's a wealth of studies, and this has been very focused on research that I've been involved in, but there's lots of work over a decade, and most of it is publicly available, so you can look at it and use it. And yeah, some of the things that I'm most excited about are moving beyond N2O, quantification and mitigation, looking at N2O by design, looking at at scope 4 emissions and other more innovative ways and synergies and how to do the most good. Yes. So that's it. Thank you very much.
I guess the first thing to say about the UK water sector, which is going to be my focus, is we've learned so much from the work that has been done by Nerea and others in Denmark, and also by the Swiss, by the great team, the Lexa Wenzelgruber and the Airwag, and of course all of the ongoing work we continue to learn. So yes, thank you for your contributions. So I will try to not speak too fast. I have too many slides, but hopefully some of the information might be useful to go back to. Not this bit, which is just I'm an old young water professional. So I started out in Australia. I've been with Jacob since 2008, and I've worked in consulting and some site work my whole career, always in primarily in wastewater treatment. I enjoyed studying, and I found that yes, diversifying my understanding of things like water law and policy has really given me the courage to do different things in my career. So yeah, this is just a little. There's been a few different waves of things, and but I guess as I mentioned to Lawrence, I changed direction from being, I guess, a normal process engineer designing wastewater treatment facilities or water resource recovery facilities around about 5 or 6 years ago. I think it was after I had my second child, and I realized that the climate crisis wasn't something that I was really helping to solve in my day job. And I also kind of started reading more about circular economy, and recognized that this planetary boundaries framework, which Nerea mentioned as well, and I really decided that I wanted to focus on this and that try to have an impact in doing good in my work in the water sector. And I guess what I quickly realized was that those direct emissions, so I'll talk a bit about scopes here as well, and hopefully Nerea has given a great overview. But the wastewater sector, those direct scope 1 emissions, mainly nitrous oxide and methane and fuels we burn on site, they fall in the waste category. And this is like the national emissions for the UK. Every country does these reports. And in that 5% waste emissions, most of that is landfill emissions. Only 1%, so 1% of UK national emissions approximately are from wastewater treatment in terms of nitrous oxide and methane, those direct and combustion fuels, direct emissions. But I guess I quickly realized that with all of the, water resource recovery work, things like water efficiency, sustainable fertilizers, more efficient water use, and in particular heating water and using water in our homes, I realized that we can really, in the water sector, impact over all of the categories of greenhouse gas emissions in any national inventory, whether that's things like biogas or biomethane. I'll come back to water heating in the home, but I realized that the circular economy and resource recovery really gives us an opportunity to act well beyond that small contribution that we make. I won't dwell on this anymore because Nerea has given a good overview. This is a nice Iowa guide that was produced by a group a few years ago now, which gives a little more detail on greenhouse gas emissions specifically from wastewater. But today I'll talk a little about both, all of the water cycle. Nerea's also done a good job of introducing these figures. I always like to show them because they're from the IPCC Working Group 1 reports, and I struggle to find them sometimes, so I put the link there. And I think this just shows it's not specific to wastewater in the case of methane, it's landfills and waste. So it's that full waste category. But it shows that our scope 1 emissions of nitrous oxide and methane are a significant source in our national methane, in our global methane and nitrous oxide budgets. But to Nerea's point, there are many other sources as well. And how do we understand these in context and recognize that everyone needs to reduce emissions no matter our contribution? But how can we support doing that most efficiently, I think is a good question for us in the water sector. So in the UK, there was a really progressive, at the time, net zero route map developed around 2020. And this was by an organisation, Water UK, and work done by consultants. Some great colleagues at Mott MacDonald were involved in this. And it had a go at scope 1 and 2 emissions, and set out a route map really, and it was quite progressive at the time, and I think provided some initial understanding for the water sector in the UK as to where they were and where they might need to go in order to get to net zero. And they've made a commitment to do that by 2030. Now, this is only for some of the emissions, and I think there's been some, I would say there's been a little diminishing of that, but there's still a lot of good progress. And I think that route map is being kind of re-estimated through ongoing work. But I guess one thing to note is also that the carbon accounting workbook, or the core, has existed since 2009, and that was developed by Acquia, which is kind of like a collaborative industry research organisation, and it allowed water companies, water utilities, which are largely privatised in England, public still in Scotland and Wales, and Northern Ireland. But this carbon accounting workbook allowed operational emissions of, for example, methane, nitrous oxide, electricity use, energy use, and some chemicals use to be calculated. The emission factors that were being used in many cases, particularly around methane and nitrous oxide, are not very accurate. But it's been around for a long time, and the sector's actually been accounting for their operational carbon emissions as best, in a pretty meaningful way since 2009. So I think that's quite interesting to know. But Acquia, since realizing that those methane and nitrous oxide emissions were really not being well estimated by this carbon accounting workbook, really initiated some projects which have happened over the last number of years, and I've had the pleasure to be involved in some of those. And then the regulator, Ofwat, which is the financial regulator for the sector here in England and Wales, really set out some kind of net zero principles, undertook a net zero technologies review, which we helped to support. And now there's quite a large amount of funding, 270 million worth of funding for England and Wales. And there's also nice work going on in Scotland through different funding. And that's to reduce, in particular, greenhouse gas emissions of nitrous oxide and methane. So that's 270 million pounds over a 5-year period. And it's going to be across 275 treatment facilities. So it's been quite a lot of work and quite a lot of progress, which I think is really positive, but there's still a lot to do. There's also some open groups that have been set up over the years, and I think there's some nice collaborative forums that are available for us to talk to each other and learn from each other. And then the final thing to note is that companies, water utilities, do have to report both their operational and their embodied carbon, or capital carbon, associated with new construction schemes, but this is still work in progress. So this is just a briefly for the route map that I mentioned. So this is just Scope 1 and Scope 2 emissions. It doesn't include any Scope 3 emissions, and the sector's now trying to incorporate these. So this is work in progress. The nitrous oxide emission factor is underestimated here if we update it to the IPCC figure, which is perhaps the best estimate we have right now. We can see that the drinking water and wastewater emissions are our key sources. We can see that utilities generate some renewables and that they also purchase some green electricity. But this is the kind of drinking water and wastewater related emissions, as at a high level estimate. And I think this is a good point to remember here is we should, no matter how green our electricity grid is, this was a point in time, and in the future the electricity grid will really diminish to very little emissions here in the UK. But we should always try to save energy, because this is saving money for citizens, even if it's, even if this is renewable energy. So there's been some really progressive reporting that's evolving, I would say. So this is Severn Trent, one of the utilities in the UK, and you can read their report online. They report Scope 1 and Scope 2 using a combination of that carbon accounting workbook and some of their own measurement for nitrous oxide emissions. So that's been a real development, and as a result, their Scope 1 emissions have grown a lot from what they would have otherwise reported in using a lower emission factor that we know wasn't correct. They report a little bit of Scope 3, but some chemical, this is changing, and now capital programs will need to see that the embodied carbon will be reported there as well. And Nerea mentioned avoided emissions, or Scope 4, and these are also very exciting. I think showing them separately, in this case, it's just electricity, renewable electricity and heat, but we're seeing the utilities all have to report their emissions, and gradually the picture is getting more complete there. I think this is not from the UK, but actually it was a nice piece of work by Vanessa Paravancini and some Danish utilities. And I think it highlights the importance of the green and the blue, which is the process emissions of methane and nitrous oxide, but also the embodied emissions. The grey there is embodied emissions in the sewer network and also the wastewater treatment works. And the pink emissions are electricity consumption and electricity production. So the embodied emissions of existing assets are significant. Obviously, they're already in the ground, but I think we should be, we also do need to think about the new construction assets that we are building. So this is some work that we do on embodied versus operational carbon using carbon estimating curves. And this is a scheme which is introducing chemical dosing for phosphorus removal, so ferric and caustic dosing at a wastewater treatment facility. And what we see is that, if the scheme takes a year or so to build, then those 333 tons of carbon dioxide equivalent in the table at to the left, that is a lot of carbon, and that all happens in year 1 or year 2, depending on how long the process takes the project takes to build. But 92% of, if it lasts for 50 years, which our civil concrete assets should, mechanical assets, we assume they get replaced along the way. But 92% of the lifetime emissions are from the chemical that is being used, the chemicals that are being dosed in this case. And so we should think about efficiencies there. And although we only have to build the scheme once, I mean, all of those emissions happening in a single year or two, like we know with climate, that the sooner we impact, the lower the future risks. So although if you spread those embodied emissions over a 40 or a 50-year asset life, they are all going to happen in the next year or two, which is, I always think of my little 7-year-old, and they're going to happen within a year of his life, which is a significant part of his life, and they're going to have a big impact. So the more that we can do to reduce those, the better. This is just some examples of lower carbon concrete, so we can maintain compressive strength and reduce the embodied carbon in concrete, and also timber. This is a dosing kiosk made from timber, and versus when you compare that with GRP, we see whole life carbon savings. And this is something that some of the utilities are looking at here in the UK, which I think is quite exciting. And it's also a really beautiful timber dosing kiosk as well, I think. Just quickly, I think it's important to note that say 4 or 5% of national emissions are heating hot water in the home, and water efficiency. We should never, perhaps as water professionals, we often get quite excited about the technologies and the processes, but just the act of reducing water use is so important, and something that we should remember will have a really big impact on emissions. And of course, countries like Australia, where I'm from, and the UK, where I currently live, are under really acute drought challenges right now. So the less water we use, the better. And there's some really cool, data-driven, interesting ways of sensors and measurement, reducing water use. Just a point. So briefly, just going to, as I finish up, talk about the different measurement. There's been measurement work for methane happening in the UK. This has primarily been with primarily a few utilities are really leading the way. So optical gas imaging or other point source quantification, some drone work with a company Explicit based in Denmark, and some continuous methane monitoring, which has really helped pick up on leaks. The way we can quantify these emissions is challenging, but the sector's really realized that if they're losing more than 4% of their biogas, then they can't really call it green. And actually, we may be losing a lot more than that. So there's a big push on right now to make sure that the biogas and biomethane that is quite, has been prioritized through many incentives over the last number of years in the UK water sector. Making sure we're not leaking that is really, really important. And right now there's not really enough measurement going on to know that we aren't leaking to the extent that we might as well be burning fossil gas or natural gas, which obviously we don't want to. There's different methane mitigation strategies that utilities are looking at. Nerea's talked a lot about nitrous oxide. This is some work by Severn Trent, who've really made a good effort at some long-term measurement, and we can see lots of different emission factors for a number of different long-term campaigns there. So that work is very much ongoing. And there are forums to share knowledge in that, which is good. Some of the challenges we have, and I realize I've just got 30 seconds or so left, Lorenz, but we have these plug flow nitrifying only wastewater treatment facilities, which is challenging. And we have a lot of anaerobic digestion, which means we have these side streams that Nerea talked about, which are quite high in ammonia, and can have quite significant nitrous oxide risks. So we have some challenges that are maybe different from, for example, the Danish sector, and we're at an earlier stage of learning here. So there's still a lot of work ongoing, but happily progress being made. I'm going to skip over this, but I always like to remind us that the nitrous oxide comes from the nitrogen in the protein we eat. I think I've talked through some of these lessons as well. There's lots of gaps. Lots of gaps, but there's now funding. So that's super exciting. And I did mention that figure earlier. There's funding to mitigate nitrous oxide and methane now for a few companies. And there's a recognition that there's business risk and financial risks for the companies if they're underestimating their emissions, and if they're not, if they don't have a meaningful net zero strategy, because there is legislation for net zero here in the UK. There's lots of fun innovation projects, which I won't have time to talk about, but there's a nice innovation fund, and the idea is collaborative innovation. A number of those are around nitrous oxide and methane, some around capital carbon and carbon reduction as well. And really there we need to be looking at kind of full life cycle analysis, and not just focusing on carbon as well, I would say. There's exciting technologies where we can link bioresources and advanced thermal conversion with drying and different ways of lower energy drying and getting more biogas where we can. And these are also kind of innovation projects. And just to finish up, I think we really need to think about carbon, but also to think about wider life cycle analysis impact categories across all of those planetary boundaries. And there's some really nice work that's been done also in Denmark and elsewhere around trying to apply that. And that's really what we're focusing on here in the UK for a number of these innovation projects, is trying to best quantify the impacts so that we can avoid just that carbon tunnel vision and try to think as holistically as we can. Sorry, I'm a little over time, but thanks very much, Lawrence.